I'm first of all going to talk a bit about statistics, then we'll, through some experiments, try to understand what I mean by, first of all, what a mathematician wants to understand in statistics, and then what a statistical inverse problem is, which is a certain class of very, very important in practice problems in statistics, and basically if it doesn't have statistics in the name, then in applied mathematics and engineering and so on. Okay, so first of all a question for the audience. What do you understand by statistics? Can someone give me a one or two phrase long answer to that?
The art of lying people?
The art of lying to people. Okay, but that's just general. So anyone?
Making sense out of complex data sets.
Yeah, that's very good. That's very good. That's exactly. I think is basically. It doesn't need to be complex, but yes, it's basically making sense of data, right? Trying to extract information from data. That's really the first idea that a statistician has. So there are a number of questions that concern people that work with data, and these may be, for instance, how to take the actual data at first, how to analyze the data, how to make the conclusions, or how to make this, how to do it fast, right? So these are different sort of scientific goals that we all have, but I will not be focusing on all of them, okay? So I will only talk about a few. Now, right, I think it's probably best to just start introducing some examples so that we understand what the kind of questions I care about. And let me ask another question. So who here has or uses Netflix or something similar to Netflix? Okay, so not many people, but I'm hoping the rest know what Netflix is. Okay, so essentially this is, of course, it's a platform where you have videos, perhaps more series and films, and such kind of documentaries and so on, and what you do when you sign up is to, of course, give some personal data to the website, and then you start watching series, right, or watching documentaries or whatever you're interested in, and you see that as time progresses, you start getting proposals of what you want to see, right? So now, have you ever wondered how on earth they do these kind of things? How do they basically think, well, this may interest you or this may not, and so on. So an idea that, well, anyone has any idea about this, how you would go about?
Tags. You put tags on whenever you watch something, they recommend you a film or a series with the same kind of tags.
Okay, yeah, a tag.
Labels.
Yeah.
Labels.
Or label it.
A thing called cookie in your local browser.
But that would be perhaps not so much for
browsing history.
Exactly. So you may have browsing history, but does Netflix use that as well? Because
I think that the cookies used everywhere. As long as it's a browser.
Good. So we've got even more information now. So we've got not only what you watch, but also what you sort of search on the internet, right? And with all of this information, now the question is, how do I propose a new film or a new documentary or whatever? So an idea that one can have, which is more or less what is done, so I will always be very hand-wavy and these kind of things, I'm not going to be very rigorous in general, but one idea that one could have is, well, this site in here actually watches very, very similar documentaries, right? And we have the odd one out here that actually does also watch very similar things, but he hasn't watched a certain new documentary yet. So then a good algorithm would try to say, well, let me, from similar people, understand whether they've seen this documentary, whether they liked it or not, and then from that recommend him, to watch it or not, right? So this is the kind of way that people sort of extract information, right? So we have some data set that informs us of something, and then we get a new observation, and then we try to make sense, of what this person likes, just using similar sort of people or sort of what people like, right, in this group. So that's a statistical problem in the sense that, of course, there is variation in the data. You don't know whether that's going to be right? So you first of all need to get an estimate or a hypothesis test, for instance here, which is basically saying, is he going to like this or not, right? So that's basically, that could be phrased as a hypothesis test in statistics. And then, so that would be the first question that you ask. So how do I know whether he likes it or not? But you can also ask many other questions like, how many people do I need to have seen in order to be very sure that he's going to like this film? So to what, you know, what is this number of people? What is that, so that I get, say, 0.1 error in my estimate, for instance, right? 0.1, I mean 10%, you know, sort of certainty of getting the right answer, right? So that would be one question. The other question would be, well, I now have an algorithm to estimate whether he, or to test whether he likes this new documentary or not. But what about a different algorithm? Will it do better? Will it extract the more information about the data, right? There is something called, well, there is something that is a mathematical concept. That is a limit in the amount of information the data has, okay? And only some algorithms will exploit and will get to that theoretical limit, basically, and give you as much information as you can from the data, right? But some algorithms will be suboptimal. So there is a fair question there as to whether your algorithm is working, you know, is exploiting all that it can from the data. And that is a mathematical question, because phrasing that is some very, very mathematical sort of, you need some mathematical language to explain all of this, right? Anyway, so that's one, that's some questions. Now, the other questions is this uncertainty quantification, right? So how can I quantify the uncertainty of not knowing whether he likes the documentary or not, right? So these are the kind of questions that I'm concerned with in general, okay? And you'll be thinking now, well, you've been talking about Netflix, but Netflix, you know, I don't care if they get it wrong. I mean, it doesn't matter, right? It's only, you know, they lose money, then maybe if they never get it right, then eventually go into bankruptcy and whatever, and who cares? It's just a company, right? But we can get much more serious and talk about cancer. I know people here are researchers in cancer, and then, you know, in these kind of things, you really want to know answers. You really want to quantify the uncertainty. You don't want to tell someone that they suffer from a certain disease when they actually don't, right? So you really want to be very precise, and therefore these questions are very important, I think, in my opinion. I mean, we care about these. Other people will care, or engineers or computer scientists will care a lot more about the speed at which you give answers, which is also very important, right? If you want to tell someone whether they suffer from a certain condition, you don't want them to be waiting for a week, right? You want to tell them as fast as you can. So those are very important questions, but they're different. I won't be talking about this, okay? So, so now that we have a bit of a picture of the questions I care about, let's do some experiments, because I want to basically show you eventually what an inverse problem is, what a statistical inverse problem is. And we're going to start from literally the most basic statistical experiment that people tend to do. And for this, I do need two volunteers. So anyone who's happy to do this, just please stand up or come here, or maybe come with this. So if anyone else, you said it's easy.
I think
you're next to me.
as well.
So any other person who wants to be a volunteer, please come and sit here, probably.
Okay.
Because then I can interact with you a bit easily. So the very, very high-tech experiment involves a coin. And we're gonna have, right, so you're gonna get the coin, and you're gonna get some paper. We're gonna need, no, actually, you need the board. You're gonna have to be somewhere there.
Yeah.
Yeah. Now that I think about it. Okay. So you just sit anywhere. Yeah. I need a bit of actually I need interaction between you two. So somehow you need to communicate. Okay. So you've got a coin. You're gonna flip it now a number of times, so you're going to be taking notes as to what she's getting, basically, right? So that's fine. Let's see. Okay, fine. Okay, so you start literally flipping it as many times as you can, so it doesn't need to go very high or anything. Heads. So let's do heads and tails columns. Right, probably slightly. Yeah, exactly. And then just literally just cross.
Yes.
Right? Okay. So one heads.
One tail.
Right.
Okay. Tails. Heads.
Okay, so while I let you do it, let me start, talking to the rest and say,
Tails.
now the question here is the coin biased, right? That would be the first question that one wants to ask, or is the coin fair, in other words, right? So now that we have, how many do we have? 6, 8. I get my glasses probably for this, that I
Tails.
don't miss things. We stop at 10, yeah? But I think we've done more or less, yeah.
Tails.
And that one we're not
Like-
taking a roulette.
Okay, well, actually, this is very good. So, okay, so now from this, how would one try, well, answers. Is the coin biased? First question. And second, please argue it. As in, why is it or why is it not?
I mean, only with this small data set you can say, okay.
But
It
did you see
looks
the
like-
coins? Did you see the
I
You
haven't
cannot
seen
take
it.
a coin in theory.
So we haven't seen the coin, but just only with the data,
Mm-hmm.
and the statistics says, okay, the probability is half and half.
Mm-hmm.
But I mean, just only using this set of data, it looks like it is. But we don't know. We know it's not.
So that's
You probably not
Yeah,
enough data.
it's not.
This
It's
sounds
not
like
enough
very
data.
small.
okay.
To
So
be fair, I
yeah.
dropped the coin once on the ground. I didn't
Okay.
see how it landed.
you change one of those, or it's okay. It's okay. So I mean, that's a great remark
It's something
because
called I don't know if it's something called the big numbers law. So
The-
more chances you throw something.
it's the law of large numbers. Yeah,
Whatever.
exactly.
Yeah,
So-
the law of like
Yeah.
that's numbers.
So, yeah, so that goes back to one of my questions, right?
Mhm.
How much data do I need in order to be certain about my estimate,
Mhm.
right? So, I mean, leaving that aside for a second, your remark, now, can we at least have an estimate of what the probability of the coin is of landing heads, for instance?
I think it's 50.
The theoretical one is 50.
An estimate
An
from
estimate.
looking at the data.
From looking
I
at
mean, you could look at the data and completely ignore it and tell me that it's 0.5. That's fine as well. That's still valid. But
2080.
So,
Right.
so the point is that you could take the data from every time that you flip the coin,
Mhm.
and theoretically it should give you 50-50. But you could just see the data with this sample, which is a bit small, but
Mhm.
you can maybe mix them both.
Mhm.
So I don't know how you,
Wait, mix what exactly?
because so the chances are really 50-50, I guess.
Unless it's a trick coin.
Exactly.
Yeah,
Unless
fine.
it's
Zero on one side.
so you.
I'm just asking whether. Well, first of all, can you give me an estimate of the probability of landing heads? First of all, then I agree that the next question is, how certain are we of that estimate? For which we need data.
The variation is not necessarily in the coin. The variation may be in Lena's technique of flipping it.
That too.
Yeah.
That too. So I'm literally just accepting that she's the best coin flipper on earth. She literally gets it. So the experiment has been performed under every single regulation that we have, to be sure that it's right. Basically, that's how we've done the experiment.
So basically, it's 28, right?
Right. So that's the first.
That's what you want to hear, right?
That's the. No, so there are several answers because the 0.5 that you said is actually an answer. So you could just stick to your beliefs and stay with that. That's one answer. The other answer is actually just saying, well, let me propose. So this we're going to have some probability p, okay, which can be 0, 100, or 50%, or 25, or whatever it is, and then this is going to have 1 minus p probability. Right? So if we measure it, 1 means 100%, by the way, for me. Okay? Sorry, I will probably forget about this. But anyway, that 1 means 100%. Okay? So now the question is, I was going to say, okay, so how do we estimate the p? So we said the p may be, in this case, approximately 2 divided by 10, right? So now I have an issue because I put Roman numbers, but so that's 1/5, yeah? Okay, so that's a 20% chance, right? So, okay, so now we say, okay, so I'm not sure about this because I am a very respectable man and therefore I'm obviously not going to use a biased coin. So, does anyone have coins, by the way, in you? And you can just flip literally like a couple of times each of you and then we can compute what comes out of it. So we're really poor in this college, clearly. you don't need to. Right, you get one.
Be a euro.
Thank you.
Right.
I think
It's okay. You don't need to take many. I literally just want to. Yeah, exactly. Just literally start flipping coins and then tell me what you got in total.
Go ahead. Espérate, que soy zurdo y me tocan.
Okay.
Head.
So you guys give me some numbers of what you got, basically. So how many heads?
Only one. I just.
Okay, one.
One.
How many?
Minimum.
3 tails.
3 tails. Okay, so we have one head here. 3 you can now stop and just tell me the numbers because otherwise we're gonna go for
Two
it.
tails, one head.
Okay, 2 heads.
2 tails, 1 head.
Sorry.
Yeah.
Yeah.
2 and 2.
2, 2.
3 tails.
3 tails.
1 head, 1 tail.
Head, tail. Okay. 4 and 4. 4 and 4.
Okay.
See, I did it properly.
1 head.
Anything else?
1 head.
6 and 1 head. Okay.
2 heads.
Okay, we can stop now. We're
No.
gonna keep on forever with this.
If you want another head,
No, okay, so let's see. Let's look at what we get. So we've got 7 here. Then now you can see me adding up, which is not a very good thing.
That's
to
why
do.
you
Public
need Roman
internal- Exactly. That was a simpler method. So now, so we've got what 12. Okay, so that's 20. Okay, so now we're getting right. So the new estimate. So that was the first estimate. No, actually, I cannot erase that. This is not a board. So now the new estimate would be 14 over 20, which is something a bit closer to, sorry, not 14 over 20, over 34, excuse me. Right? Which is actually closer to 0.5. Okay? And this was not biased, by the way. It just turned out to be, this is what is called an excursion in probability. So suddenly your random process starts doing something that you weren't expecting that has, well, in this case you weren't expecting. It's just, and this is just as likely as having seen 5 heads and 5 tails, by the way. But anyway, so now we've got this estimate. So you gave me, what you gave me here is what is called the frequentist method to estimate the probability. So this is excuse my writing, frequentist. Okay, a frequentist method. Why is that? Well, we're just looking at frequencies, right, of what we're getting. So now the next question is, of course, what you were asking. As we get more data, are we converting, or are we getting closer to the actual value? And we see that in this case we are. Then the other question, which is, so the other question here, which is very important, is this the best way to extract the information from the data? Okay, I will not go into that, but basically it is. In this very simple experiment, this is the best way to estimate the probability of the coin. Okay? Now,
but it doesn't have any bearing on the answer to the question of whether the first coin was biased.
No.
No.
Well, so assuming all the coins are equal, then
we must. Yes.
then we can infer and have a central limit theorem that tells you, you can quantify the uncertainty, basically. But but this is a 50p coin, like just a normal coin, basically. Okay, so let's do another experiment now. So you're going to need now something else. So I have a few dice in here to play with. And I don't remember the order I need to take them in, but it's written in my hand. So you need to take the red now. Let me
brilliant.
just say. Okay, so right. So now same experiment. Can you start just sort of rolling the die, and you start sort of actually just put
How many options do we have?
3, 4, 5, and 6. Right. I'm going to change. Right. How many did you get, or just carry on doing it
Okay.
like 10 times? Yeah, 3.
3.
Okay.
3. 3. 5. 3. 3.
I should have crossed it a while ago, but anyway.
3. 3.
So how many streaks do we have?
5.
5. Okay. So, now a question.
Why is,
is
why is there more than one face on that die that says 3?
you guys should not be looking at what she's doing. Anyway. Okay. Right. What do you think? Is the die biased in any way? Is it
Yes.
not?
Perhaps.
It is.
Probable.
Right.
Perhaps.
But would you be able to answer the question of, is there any probability of getting the 1? Or is there any probability of getting the 2, the 4, the
No
6?
idea.
Perhaps we didn't have.
To-
We didn't wait enough. to-
Yeah.
Right, so still we're sort of going through the same concept of needing a lot of data to be certain about things, right? So this is one very, very important question that we try to answer. This is what is called convergence rates, okay? So we're trying to understand how fast the frequencies that we observed before are actually going to the true value, in this case probability of the die, giving you a number 3 or giving you a number 5. Okay, that was a question maybe?
No.
Okay, right. So I think we got basically 8 over 10 here. So that's 4 over 5. And then 2 over 10, which is 1 over 5.
Seems corner.
Very good. Very
No,
good.
but there are 6 sides.
There are 6 sides.
Right, so it's not the.
Well, no, but she said it's the same as the first experiment we did, basically, yeah. So, okay, fine. Right, so we've got this experiment, which was simple. So now what we've seen, what we've concluded, actually, or well, I can tell you that you can conclude that, is that this is a die with only 2 numbers in it, which is number 3 and the number 5. And the probability of each of them is basically, so that's going to be the P1, and this, the probability of this is, what was it, 4 over 6, so that's 2 over 3, and then P5, sorry, that's P3, I want to say, and that's 1 over 3. Okay, so we really didn't get, well, we didn't get too close, but at least we didn't get something too surprising given that, right? Okay, so from now on, I'm going to be using these kind of dice, basically, so I have more of them, and I can tell you already that they all have just 2 numbers, okay, no more than 2 numbers, with different probabilities in each die, okay? I'm not going to tell you what probability in each of them, but you should consider from now on these things as biased coins, okay? Don't consider them as die, just simply 2 options, that's it, okay? And I don't want to show them to the people, because otherwise you're going to cheat, otherwise. Okay, so next experiment is going to get a bit harder now. So now we have biased coins.
Probability of you from.
So now we have biased coins, right? So we use, by the way, the frequentist method again. So we're looking at frequencies. And now I'm going to give you a bit of a harder problem to see whether you can use these frequencies or not, okay? Okay, let's, what is it? Green, I think it says. Okay, so green. You get the green, what was the experiment? Wait a second. Right, yeah. So don't show it to the people, no. And now what we're going to do is you're going to roll the die, basically, okay, you're going to roll the die, and every 2 times you're going to say the addition of the numbers that you got. Okay, so she's going to get 2 numbers, and then she's going to add them up. And she's going to basically report this sum of the 2 numbers every time. Okay? Right, so you start doing things, let's say. So, okay, now we've got an issue, which is, what are the options? Okay, oh, sorry. Before you forget what you got.
8 was the first one.
Okay, 8. Okay, so let me design the experiment slightly differently, because then it's going to be easier for everyone. So that's going to be a 0, and that's going to be a 1. So you got 1 basically now, right?
Okay.
You got 0 plus 1.
Okay.
Right?
Okay.
Okay.
Yeah.
So 0. So take it as 0. So the smallest number is the 0, and the largest number is the 1. Okay. Okay. So we only have 0s and 1s. That's like the coin, right? 0 and 1. Okay. So now in the first, so the question is, with the coin that you flip twice, what are the options of what you can get? Well, you can get a 0, you can get a 1, and you can get a 2. Right? The 2 is just 1 plus 1, and so on. Right? Okay. So we can get only the 0, the 1, and the 2. And you said we got one of these, a 1, and then just go on doing things, basically.
0.
Okay.
0. 2. 0. 0. 1.
I think we've called 9, yeah?
1.
Okay. Right. Okay, so what do you say now? So we have a coin, remember, we've got a coin with a 0 or a 1, and there is a probability that may be 50% or not, and we're only observing the addition every 2 times, right? Every 2 flips of the coin.
I think it's biased toward the 0.
Okay, so that's a good first observation, yeah? And then, I guess, one way, well, sorry, does anyone want to say anything, by the way? Any ideas?
So, if we're pretending this is a coin, right?
Always go, yeah.
So, the fact that we're looking at the sums means we're talking about the likelihood of 2 events happening consecutively.
Mm-hmm.
Okay, so it's different from looking at just an independent, each time you flip the coin.
Well, each of the experiments will be independent from each other.
Okay.
I guess you do mathematics, so I can talk. I think you don't.
So
You
it's
know
like a
mathematics.
permutation rather than.
Yeah, but they're all independent draws from a distribution that basically tells you
Okay.
whether you can be 0, 1, or 2 with certain probabilities. That's exactly what it's going on.
No, I don't study math.
Oh, okay,
But
sorry.
it's just,
Then maybe
it's,
it went a bit
it
far.
looks very
but-
similar to
yeah.
the other.
It's very, very similar. It is.
So
The issue here is that we're not observing directly the coin, right? Which was then giving us a very straight answer, a very straightforward answer. While here it's not that easy, right?
I can guess that maybe it's we've got two 1s and 4 zeros, something like that.
Right, so you're trying to guess what happened,
Yeah.
but I'm trying to guess what the probability of the coin being heads is, basically. Because then once you do that, you can then predict a bit what's going to happen, right? If you knew, so before we were trying to understand whether it was biased or not, and then we were trying to understand the bias in the second coin, which was a die.
Yeah.
So now the question is, can we understand the probability now from this? Again, this biased coin, can we know the probability of each thing? So let me just here, so we have, just to reiterate what experiment we have, so we have a 0 or a 1 in the coin, and for the 0 we're going to have a p, which is again between 0 and 1, so this is, you need to multiply by 100 if you want to know the percentage, and then the other one is 1 minus p. So really the probability of getting a 0 would be getting a 0 and getting a 0 again, right? So we need that. So therefore the probability of this is p times p, which is p squared. Okay? And the probability of getting a 1 is getting a 0 and getting a 1, but we could also have got a 1 and then a 0. So therefore this is 2 times, well, this is p 1 minus p, which would be getting that, and then getting the other one. So getting it in the opposite order, so this is just 2 times 1 minus p. Right? And then what is the probability of these two? Is we can only get it through getting 2 1s, so therefore it's 1 minus p to the square, right? Which is the product of the 2 options. Okay, so given this, can someone still give me a guess of how to estimate p? Do you know when we started, by the way?
Quarter past.
Past.
Is the
Sum mark equal to 1.
Which of them? These or
P
those?
squared plus 2p times.
So if you sum up all of this, then you're going to get a 1.
Yeah.
Because there are no more options in the experiment, and therefore it's the sum of all the probabilities, right? But my question is, can you estimate the value of p? So p is what is driving the coin, the underlying coin, is what is driving whether you get heads or tails. And let me call this heads, by the way, and that tails. And then the question is, can you have an idea of what p is from this information that I gave you?
Well, you could say p squared is 6 out of 10.
Yeah.
So the
Okay.
square root of
Right.
6 out of
Exactly.
10.
So that's one excellent guess from here, right? So you say, well, p. So this guy here, this is 6 successes in this experiment, and we have 10 experiments. So therefore, the p square is going to be more or less 6 over 10, which is 3 over 5, right? So therefore P may be approximately 3 over 5. Oh, sorry, the square root of that, yeah? Which is less than 1, of course, and this is, this is something that is a reasonable guess, right? You may also use this, for instance, right? And say therefore that you can work it out from here, and you may get a different value actually for the estimate. Okay, I don't know if you will in this experiment, but maybe there might be experiments in which you get that. Okay, so now the question is, right? So this is an estimate. So if you get more and more data, will that go to the right number?
Maybe.
Probably, yes, I can say probably. But can we do better than this one? Because note that you missed information, right? So you didn't exploit the fact that we had ones and twos separately. So you only exploited that either you get a 0 or you get something else. But there is more information in there, which is that actually what wasn't a 0 was a 1 or a 2, and they give you different ideas of things, yeah? Okay? So this, I can very, very surely claim that this is suboptimal in that sense. So it will not exploit all the information from the data, basically. But now building an estimator or building a way to estimate the actual P from this data now gets a bit more complicated. Okay, so I'm not going to do it, basically, but it gets more complicated. So now, should we just take the experiment slightly further? You're going to now start rolling again, and now we're going to observe it every 4 times. Okay, so you're going to add up 4 times each, or 4 rolls, or rolling, or whatever you say, and then we put the numbers here. So what are the options that we can get?
0, 1, 2, 3, 4.
Okay, so we can get up to 4. Yeah. Right. So 1, 2, 3, and 4. So is everyone with me up until now, by the way? Right? Haven't lost anyone? Okay, good. Right. So if we think of the previous idea, then the 0 is getting 4 times the heads, so that would be P to the 4, right? And so on. We can get some numbers here that are going to look a bit complicated, but we can get basically this number. So what did you...
1?
Yeah.
0.
Yeah.
1. 2. 1. 0.
It's the same die.
1. 2. 1.
Okay, we can start now.
Okay.
It's fine. It's 9, but it's okay. This still illustrates my point because basically now we have a lot more options than before, right? So it's the same die, so we should be somehow being able to get an estimate that is similar for it. But now if we try to, so if we use your method from before, we get an estimate and then we'll be missing 4 things of information, 4 boxes of information. That's a lot of information now, right? Before we were only missing 2. We were missing actually 2/3 from the information. Now we'll be missing 4/5 of the information, right? So that's a lot of information that we're missing now. So we need to sort of play around with all these things in order to work out a new estimate for this problem. But what I want to illustrate with this is that the problem is getting more complicated. For what reason? Well, the main reason here is that we're starting to spread the data across several outcomes of the experiment, and each of them is going to give us one piece of information. So really we're starting to lose information, we're starting to spread the information, and therefore if we have 2 die that look very similar, then the answers here would start looking similar as well. We wouldn't be able to difference between things, and what is happening here is that this problem is becoming an inverse problem. Okay, so little by little, if we kept doing this, it wouldn't be exactly an inverse problem, but it would be close to it. Okay, and the reason is that we're no longer observing something that gives us directly the information that we're looking for. Okay, so in the first experiment, we had this coin that we could observe, and we could tell, straight away how many heads we had, and therefore just take the frequencies and so on, right? Here, little by little, we're starting to lose sort of that intuition, and we cannot apply the other methods. So I had basically a last experiment that we don't really need to do, because I think that the point is very well illustrated already. So that's blue and white now in this order, which would be you rolling this one and me rolling this one, which are two biased coins. And now what we would get is, instead of doing this every 2 times or every 3 or every 4 times, we'd do it every number of times that the die tells me, which is then a random number of times, right? So we don't really even have this information as to, we could also work out, these p's, but it would get a lot harder, basically, because we wouldn't know how many times we've rolled the die, basically, or flipped the coin, right, for the answer that we're getting. Okay, so that really is now an inverse problem. It's a very simple one, even though it's still a bit hard to explain in the first place, but that is really an inverse problem. Okay, so now you'll be asking, well, I hope, the next question from someone, or at least what you have in your minds, is basically, okay, so how do we do it, right? How on earth do we do it, and why do I care about this? First of all, I guess.
That's my following.
Okay, yeah, sorry. So maybe I'll flip it around, and we'll start with that. Yeah, I shouldn't lose people. So first, let's say why I care about this, right? So we can picture the experiment a bit differently. Okay. What we've been doing here is essentially, so this is going to be time. Okay. So we started, of course, at time 0 when we started the experiment, and there was heads, so we're going to say that's a 1 and that's a 0, right? So there was a heads at time 1, it was heads. At time 2, maybe there was tails, and then heads, at 3, it was tails. Heads, I don't know what I'm saying now, I don't know which is which, but anyway, so let's say that this is heads, okay, the zeros. And then we sort of guessed that it was biased towards the heads, and therefore, let's imagine we've got this excursion that I said before, which is basically that we get many things that we weren't expecting, and then we get a bit of that, and then this, and then, well, actually we got unlucky, and then we got that. Okay, so this is what we have essentially in the experiment, right? Now, if you take this to, if you sort of take time here and start looking a lot more, not only these, 10 experiments, but look at 100 and look at thousands and so on, and we try to plot them just exactly in the same space, what we're going to get is something that starts going up and down, right? Then there's that, and then there's this, and so on, okay? So does this remind you of something that you've seen before? That kind of graph?
Stock market.
Right, okay. So you're there, okay. So that's exactly what one observes in the prices, in the stock market, right? So one observes these kind of fluctuations. Of course, it's going to be harder than zeros and ones, and then we'll be getting, a different picture that looks a bit more like going up and down and fluctuating a lot more than the previous, basically, okay? And in many occasions, just because we cannot observe the prices directly, or because it's just too costly to get all that data, for instance, we observe this graph, well, maybe every week, okay? And then we're given that point, and that point, and this point, and that point. And this is very similar to what she was giving us, right? Because she was giving us, every 2 experiments we get the data. And then now the question would be, well, imagine that this is actually created by a coin. Can we guess, first of all, the probability of going up? Or alternatively, equivalently, the probability of going down? And that is very important for at least 2 reasons. I mean, first of all, well, I guess the main reason is that you want to understand the market, because you may want to bet, for instance, right? You may want to invest some money.
Bet,
and therefore,
investing.
Right, it depends on how you look at it. But anyway, so you want to invest, you want to know whether it's going to go up more often than down, right? For instance, right? And these are fair questions. So this is So this is one application to what I was saying, but you could also, for instance, imagine this graph as being a population, right? A population of some sort of bacteria, for instance, growing in somewhere, right? And you say, well, actually, are they growing more on average or dying more on average? And then you estimate that, and you see that you get more and more data, and for instance, let's say you get 0.6 probability or 60% probability of going up, and therefore 40 of going down, and suddenly you get new data, and this starts to change to 0.7 instead of 0.6. And this turns out to happen when you give them a certain, when you change the protocol, for instance, or when you give them something that, I don't know, I don't want to say words that are not correct, basically, but I'm trying to look for the right word. Pardon?
Let's say treatment.
Right, so you give them a treatment, and then suddenly you see a change. And that is telling you that the treatment actually worked or didn't, and so on, right? So this is the importance in all of these things, and I basically look at these kind of problems, which is basically an inverse problem, because you don't know what happened in between. You need to undo that operation of not seeing this, and try to understand what's behind it, right?
So I would say, for example, that using the appropriate tools, I will be able to estimate somehow how a population of cells is going to behave against a drug, for example. Let's talk about the cancer cell, for example.
Right, so we wouldn't be able to tell straight away what's going to happen, right after. But we'd have an idea of whether it's going to be, on average, going up or down,
in terms
right?
of, behavior.
Well, exactly. So imagine this is a 0.6 that I said. Then you know that right here is very likely that it will be higher than here, right? That's a statement that you can say further, right? And for instance, in finance, you've got these products that tell you, well, no, actually, not in finance, in insurance. You say, for instance, well, if the price goes above $10 per kilo of, say, wheat, then I want you to pay me, the insurer, because I'm going to start. Well, maybe the other way around, but anyway. So if someone who's buying wheat, right, basically if the price goes above 10, then they say, well, now I want the insurer to pay me. I've bought this, of course, this policy that says that. And because I want to hedge against, I want to protect myself against the price being too high, right? And so these kind of questions are really, really important in many sort of fields, essentially. And now let me show you, so I have two options, basically. I don't want to go on for too long, because we've basically been going for 45 minutes. So I have two options now. One is to show you how to guess the solutions in the previous problem. So I will show you with the laptop basically the method that does this, sort of with some plots, or I can tell you about other inverse problems basically that happen without actually going on the board, so just explaining a bit what happens. Anyone has any preference on this? So I think that should be the last thing. So
may I ask a question?
Sorry, yeah,
You're
please.
using a terminology that perhaps everybody else understands and I don't. Are you saying inverse problems?
Okay.
Is that what you're saying?
Yes.
Okay.
It may be. Yeah.
I haven't come across the term. So what is an inverse problem?
It's exactly what I showed you. So first of all, we had this coin that was informing us straight away of what was happening. So whether it was biased or not, we could see it directly. And then the problem started getting harder and harder, and we couldn't see what really was giving us the information. I mean, it still gives us information, of course, because otherwise we wouldn't be able to make any conclusions. But it is there is sort of like a deterioration of the data. So we start the data. I mean, there are many sort of mathematical definitions for this, but some non-mathematical will tell you that you just cannot see directly what gives you the direct information, or what gives you the information directly. Right? That's exactly.
Okay, thank you.
Yeah. So then this is an inverse problem in that sense, because from here to here, many things happened that you didn't see actually, and they are important to estimate. So you have very little information. In that sense, is an inverse problem. Sure.
So, for instance, with the last coin experiment, I was adding up 4 times, but each time I was summing up 4 times. With an inverse problem, is each data point, if we were talking about coins, do we know that? Can we assume that it was repeated the same? Well, don't know how to ask this question,
Mhm.
but right, can we assume that there is some level of uniformity
Mhm.
about the data, even though if we don't know, let's say how many times
Mhm.
I summed up the numbers?
Mhm. So for instance, if you see this, can you assume that everything has the same type of activity in between?
Yeah,
It's
is
more or
it
less what you're
uniform?
saying,
Yeah,
right?
yes.
So I went really fast, but the last example I wanted to show you was precisely trying to illustrate that you don't have to. And in
Okay.
fact, if you don't have that, then is when it's really an inverse problem.
Okay.
So basically what I wanted to do
Right, yes.
was the blue and white. That was basically you were gonna roll this, and I was gonna roll this. So this has 2s and 4s. So if I got a 2, then you would roll that 2 times. Sorry, you would add up
Right,
that
okay.
2 times,
And
and then I would roll it again and then 4,
got it,
and you'd then add 4.
got it.
But this would be a random amount of sums, right? That we're seeing every time, and therefore you've got in some sections more activity than in others. And that's exactly what happens in practice, and that's exactly the inverse problem. That's exactly what I work on. It's these kind of things that come randomly. You don't know how the activity is behaving in each place, basically.
Yeah.
Okay.
I can imagine if this was the sales prices or something like that,
Mm-hmm.
and I can imagine if you're trying to make sense of the data, it's almost impossible. At least for me, because I'm not in your place, but
Mm-hmm.
I can imagine if you're trying to make sense of this data and the sales going up, it can it could come from many different reasons or data. So I can imagine the electricity cost, labor cost,
Mm-hmm.
political decision, instability,
Mm-hmm.
cost of the
Mhm.
cold, anything. And
Mhm.
in order to make sense of these simple data, you will have to study 100 or 1,000 different scenarios and how they behave in itself, and then open another pool of information and do exactly the same exercise with the
Right.
price of the electricity, for example.
Right.
Why is it going down?
So okay.
It looks to me like almost impossible
Right. Okay.
to predict.
So maybe this would be a good memory to show us how you solve it.
Right. So that's more. I'll give you an answer to that though first, because basically you're talking about what is called fundamental analysis. So you're looking at the fundamentals driving the price, which is basically how well your company is doing and so on. How much debt it has and so on, right? But they're all causes for a certain behavior of price. And actually, I don't care what is causing it. I only care about the behavior, right? I only care about the consequences of those causes. And then, once I observe this price, I just try to understand the probabilities of behaving in a certain way or another. So I don't really care about what is giving rise to those probabilities, which is what you're asking about. So I'm a bit closer to technical analysis rather than fundamental analysis in some terms. That's the first answer to that. And second is that I don't actually look at finance. I don't look at any applications. So what I look at is just basically, I say, well, my model is based on coins, then what can I say about it? Basically. So as mathematicians, what you do is just try to simplify the world as much as you can. Forget about that, forget about political instabilities and these kind of things, and you just say, well, let's assume it's coins, let's assume it's dice, or let's assume it's something more complicated, but still something that I can handle without these kind of things, and then let's see what I can say about it, basically. And then the applications are, of course, these kind of things that I was explaining. Other applications, basically, that you can have, well, maybe not of this, but in other. So the important thing of this is not only those applications to which this can be applied, but also the understanding that we get from this can be transferred to then other problems that are not of this form, but they're still inverse problems. So these include, for instance, MRI, these include CT, they include, for instance, when you're looking for oil in the subsurface. What you do is, and I had an experiment that I certainly cannot do because I haven't done it yet, so therefore I shouldn't be improvising now. Essentially, ultrasound, for instance, right? When they look at your some injury, for instance, using ultrasound, what they do is just to release some sound waves, and then these sound waves just they bounce in some sense, right? They bounce against the I mean, I'm being very, very hand-wavy, by the way. I'm sure this is completely wrong, but it's a first order approximation to what happens. So they bounce back, and then you need to work out what the shape of, the injury that you had is, whether you have an injury or not, right? So you're not observing directly the injury, you're not observing what is behind the tissue, and therefore it's an inverse problem. Well, it turns out to be an inverse problem, but the idea is basically that. Or you can also have, for instance, when you put, for instance, water in, so the drilling to get oil, for instance, what they do is to introduce some water, so that then they push the oil out, essentially, when they want to get some oil. First of all, you need to find the oil, right? To find the oil, you do something super hand-wavy again, something similar to what I just explained, right? So send some waves, see how those waves deform, basically, and you'll be able to tell, first of all, whether there is the material that you're looking for, and second, whether that is mixed with other materials, because they will give you different answers, basically, depending on what you're getting there. And then once you're sure about that, you do this of introducing the water, you push it out, but it's not that simple, because you may introduce the water may come with some bacteria from the surface, or it may come with something else that you add, as a product that you add, and this may pollute under subsurface water, for instance, that we want to drink, and that is not next to the oil, but is somewhere else very close. So you want to understand whether there is porosity, whether the water is going to be filtered through and then contaminate or pollute the freshwater tanks or natural tanks that you've got there, right? So that you do it precisely measuring the pressure of the water that you're introducing. You measure that, and that gives you information about how the this tank is basically absorbing the water or not. So that is an inverse problem, because you're trying to work out how the surface is, how the subsurface is, from the pressure of the water that you put in there. So it's really not directly related to what you're measuring, which is the pressure, right? And you're trying to work out the other more complicated things. So that's an inverse problem as well. And I'm not saying that by solving this you solve all of those, certainly not. But what I'm saying is that they share some common things. And by understanding this or others, then you start building a theory, which is what we're doing, essentially, to have a mathematical, first of all, framework to understand them, and second, to answer the questions of what is the best way to find the solutions, how do they behave as you get more and more data, how certain am I, right? I want to be certain that I have an injury or not, and so on. So these are the kind of questions we care about, and I think it's probably a good time to stop here. Yeah. Thank you for your attention.
Fantastic. Well, thank you very much to Alberto for making this accessible for everyone, and for showing us why this was such an important matter to be doing in the first place.
Thank you.
Real world applications. That was great.
Right. Thank you for your attention. You were all very, very good.